Today, we're going to think about integration. One of the ways that we want to think about integration is that integration is multiplication in which one of the factors is variable. We know that integration can be used to find area under a curve and above an interval on the x-axis. So we can calculate the area with the definite integral from a to b of f of x dx. This we already know. What we want to remind ourselves of is the thinking that goes behind this. We know that area is length times width, but under a function, the length is all variable. So the width is just the width from A to B, but the length is variable. So here is the length on the vertical, and length is variable. So we're trying to calculate area as length times width, but the length, it keeps changing. So I can't just multiply the length by the width. So I have to drop one level down in my operations. I have to switch from multiplication, which is repeated addition where everything is, all the terms are the same. And I have to drop that down to addition. So integration is just addition. Integration is addition. These ideas are connected because multiplication is repeated addition. It's addition when all the terms are the same. Multiplication is repeated addition, right in the damp spot of the ink. Multiplication is repeated addition. That is addition when all the terms are the same. But in our area calculation, since the length is variable, we have to drop back to regular addition where all the terms can be different. In regular addition, all the terms can be different. And so that's what integration represents. Integration is multiplication in which one of the factors is variable. So we drop that down to integration is addition, because in regular addition, all the terms can be different. What makes addition interesting in calculus is that we're not adding a discrete sum. The sum in an integration problem is a continuous sum. So the interesting calculus bit, we have in calculus, in a definite integral, we have a continuous sum rather than a discrete sum. In a definite integral, we have a continuous sum rather than a discrete sum. So what I mean is that a discrete sum has distinct terms. It's a countable sum. There's a first term, a second term, and a third term, and so on. So the discrete sum has terms that we can count. One plus two plus three plus four. Distinct terms, discrete terms. But a continuous sum, we're adding up over a continuum. In a discrete sum, there's an infinite number of terms that are infinitely thin. So the continuous sum that we have is modeled with a discrete sum. And that's why we get where we get the Riemann sum from. So the big idea in a Riemann sum is that we're just going to approximate the function by assuming that everything is constant. So we make a constant length for some small change in the width. And then we're going to add up all these little areas for however many we use. Then the continuous part happens when I divide the region up into an infinite number of areas. This is where we make things continuous. So that is where we make everything continuous. Then the amazing part is that we can get away with doing this by just finding an antiderivative of the function. So this taking the limit as n goes to infinity in a Riemann sum, that's what takes our discrete sum where we're modeling a continuous sum and we let n go to infinity. Then we go, well, now we're adding up over a continuum. It's the difference between counting the number of people in a room and measuring your height over time. Your height is changing continuously, even though, but you model it when you stand up against the door jamb and then you put a little mark to mark how tall you are. You get this discrete representation of something that is continuously changing. Because if you just stood up against the door and had the pencil attached to your head, then you would see just a continuous line going up the side of the door jamb because you're growing continuously. But you probably wouldn't grow if you spent your life leaning up against the door jamb. That's not really a sustainable thing. So we model it with this discrete measurement. Every once in a while, we just measure how tall you are. Any questions? I'm not sure if parents still do that, but I've seen it represented in movies, so I assume it's a thing that still might happen. So here's how we're going to start applying this information. Integration is multiplication in which one of the factors is variable. So anytime we're making a calculation that involves multiplication, we could turn that into integration. So any calculation involving multiplication is a potential integration problem. Any calculation involving multiplication is a potential integration problem. All we have to do is set up a scenario where one of the factors is variable in single variable calculus with respect to the other factor. So area is equal to length times width. We've seen where the length can be variable throughout over the width, and so we have to integrate. The length is continuously changing over the width, so we have to integrate. Distance is equal to rate times time. If your rate is variable for an amount of time, or if your rate is continuously changing, like if you are accelerating, your car doesn't go from 0 to 60 in no seconds. It takes some time to accelerate. So your rate is continuously changing, and the area under the curve will tell you how far you've gone in a certain amount of time. But we have to integrate your rate function to figure out your distance. Some other physics sourced ones. Mass is density times volume, or area, or length. We usually first encounter density as mass per unit volume, but density is just how much is there divided by how much space it's taking up. And the space could be a volume in the case of mass per unit density, or it could be a case of area in like a population density is number of people, how much is there, divided by how much space they're taking up, the area in which they live. Or it could be measured over length, the number of cars on a certain stretch of highway, for example. So anytime we find a multiplication problem, we can also find an integration problem. Another one that comes from physics is work is equal to force times distance. If we apply a constant force over a distance, then we get to calculate work with multiplication. But if the force is changing over the distance, then we'll have to integrate. Any questions? Comments? Snide remarks? My length got a little messed up here. I don't know why it was bothering me so much. So what's going to happen because we're going to start doing application problems, and what's going to happen is there's going to be a scenario where we want to calculate the distance traveled by a car, something that we've done before, and we want to multiply rate times time. If all the factors are constants, then we get to multiply. That's usually the way I phrase it. If all these factors are constants, if all the factors are constant, then we get to multiply. But if one of the factors is changing, if one of the factors is varying, then we're going to have to add. We don't get to multiply, we have to add. And if one of the factors is changing continuously, then we have to integrate. So if one of the factors is variable, then we have to add. If one of the factors is continuously variable, then we have to integrate. Ran out of space. So that's the hierarchy of things. If all the factors are constants, then we get to multiply. If one of the factors is variable, then we have to add. If one of the factors is continuously variable, then we have to integrate. Let's draw a quick picture of those three scenarios. So for example, distance is equal to rate times time. So to calculate distance traveled, we take the rate and multiply by time. In scenario 1, if our rate is constant, then our distance, we get to multiply for our distance. So if we have a constant rate of, let's say, make it easy on myself, 100 kilometers per hour, and we do that for 6 hours, then our distance is just going to be 100 kilometers per hour times 6, or 600 kilometers. If all our values are constant, then we get to multiply. If we have different values for a rate, let's suppose that's driving in one direction. We got to go 100 kilometers per hour, but then on the way back, and we did that for, let's say 4 hours. Then on the way back, we were driving slower. So we were only getting to go, let's say 70 kilometers per hour. And we did that for 8 hours because we took a different route. So let's put this at 12. Now we get to multiply the individual pieces, but we have to add because we don't have just one area, but we get to multiply on the individual pieces. So here's one part where we're going 100, and then here's another part where we're only going 70. So our distance traveled is going to be 100 for the 4 hours plus 70 for the other 8 hours. That sounds kind of awful. We get to multiply on the individual pieces where the rate is constant, but we have to add to get the total distance. We get to multiply where the rate is constant, but we have to add to get to the total distance. So here we are using addition. We have to drop it back from multiplication to addition. Then in the third level, our rate is continuously variable over the time. So here's where we have a function. So now, if we do have this rate to count over this rate that's continuously variable, say from 0 to 10, now our distance is going to be the integral from 0 to 10 of f of t dt, whatever that area happens to be. So here, the rate is continuously variable. The rate is continuously variable, so we have to integrate. The rate is continuously variable, so we have to integrate. Any questions? So our job now is going to be to set up integrals based on some multiplication, either just find the area, find the distance, find the mass, but things are going to be variable. And so our job is going to be to figure out how do we set up a function to model this continuously variable factor. So our job is to set up a function to represent the continuously variable quantity. Any questions? All right. That's going to do it for today. We'll start setting up some problems tomorrow, but this is the thinking that we want going behind it. We're going to be setting things up, and it's all going to come from some multiplication. Area is length times width. Volume is cross-sectional area multiplied by height. Distance is rate times time. Work is force times distance. Anything that we're just multiplying, we're going to take one of those factors and make it variable, specifically variable with respect to the other factor. All right, that's it for today. I will see y'all on tomorrow, and thanks for playing.